In this video, we're going to learn about the way that light interacts with matter, specifically those ways that utilize the wave properties of light. Why do we care? Well, we can't see light itself, but we can see the way that it interacts with matter and then with our eyes. And this is what determines how we see the visible world around us. So to understand how we see what we see, we need to understand how light can be manipulated before it even reaches our eyes. Remember how back in the first video I suggested that you pour yourself a glass of water, put a straw in it, and see what happens? If you haven't, give it a try now and look at the glass from the side. If you don't have the supplies on hand, I'll show you a picture of my experiment here. What do you see? It may look like the straw is bent from the top. It appears to be disconnected and is oriented at a slightly steeper angle compared to what is suggested it should be by the portion above the water. But if you were to go and look at the straw from the top, the straw is clearly still intact. What's going on? Well, it's an optical illusion arising from the way that light interacts with water compared to light interacting with air. So I want you to think about the last time you dove or did a cannonball jump into a swimming pool or other body of water. Did the water feel different from the air? It was thicker, and maybe you encountered some resistance upon entering the water. It's the same thing for light rays. If light was passing from air to air, it would continue in a straight line. However, when light rays move from air to water, and they hit the water at an interface hit the air-water interface at an angle called the angle of incidence. Once they encounter water, they have resistance and the light slows down. This slowdown causes the light to bend away from the surface and at an angle that is smaller than the angle of incidence. The light bounces into the medium away from our eye line. The angle that the light travels at in the new medium is called the angle of refraction, and this phenomenon is called refraction. Let's use an analogy to back this up though. So let's say we have a car traveling along the path of the light beam. It's traveling at an angle that the front passenger seat wheel hits first. However, the other wheels are still traveling at a normal speed, so they'll swing around towards the angle until they hit the water too. The result is that the car is now swung towards the water and is traveling at a steeper angle than we would have predicted. The opposite would be true if we're going from water to air. We can use a term called the refractive index to summarize this phenomenon to tell us how much a particular substance or medium slows down light compared to light traveling in a vacuum. The refractive index, or N, is the substance of a substance is the ratio, and it's equal to C, the speed of light, of the speed in light in a vacuum divided by the speed of light in a substance. So the refractive index, N, is equal to the speed of light in a vacuum, C, divided by the speed of light in the substance. For all intents and purposes, the speed of light in air is almost that of a vacuum, and it's equal to 1.003, but in this class we'll actually just use 1.00. The list of refractive indices for some common substances are shown here. Know that the larger the refractive index, the slower the speed of light is in a vacuum the faster the speed of light is in a vacuum compared to the substance. So the bigger the number, the more the substance will slow down the speed of light compared to a vacuum. So let's pause and practice now. The speed of light traveling through wool is 1.92 times 10 to the 8 meters per second. What is the refractive index of wool? Use the refractive index equation to solve. So we know that the speed of light in vacuum is 2.998 times 10 to the 8 meters per second. We also know that the speed of light through wool is 1.92 times 10 to the 8 meters per second. So to solve for the refractive index, or N, for wool, we would divide 2.998 times 10 to the 8 meters per second by 1.92 times 10 to the 8 meters per second to get a refractive index of 1.56. So refraction is what happens when light passes through a new medium and ultimately bounces away from our eyes. That light doesn't reach our eyes, it passes through the medium. But does light always go all the way through a medium? Not necessarily. Some light may bounce back off the surface. This phenomenon is called reflection. There are two kinds of reflection, and they are super important for determining how objects appear to our eye. The first type of reflection is called specular reflection. Specular reflection is when all of the light is reflected back off the surface of the object at the same angle as the angle of incidence. For this to happen, the surface of the object has to be completely, perfectly smooth. But what makes specular reflection interesting is that these surfaces that exhibit specular reflection are what we think of as being perfectly reflective, like mirrors. So my bathroom mirror is a surface that undergoes specular reflection. Specular reflection is also used in art. For example, the Cloud Gate sculpture in Chicago, also known colloquially as the Bean, utilizes specular reflection. If specular reflection were the only type of reflection, our world would look really different. So it's not possible that all light is perfectly reflected back off of a surface at the same angle as the angle of incidence. Something else has to happen too, because everything in the world isn't completely shiny, much to my sadness. This is where diffuse reflection comes in. Diffuse reflection occurs when light is reflected, but not at the same angle as which the light hit the surface, and in fact, all of the light isn't even reflected at the same angle. This happens because the surface is not perfectly smooth. It may be bumpy or have some raised spots, which causes the light to be reflected at a variety of angles. As a result, the surface of these objects appear to be matte or rough or bumpy or even just not shiny. Now, if you're wondering exactly how this ties back to fibers and dyes, I want you to take a minute and think about the last time you spilled water on your clothes or you took your clothes out of the laundry and they were wet. Did the color of the clothes change? Stop and think about it for a minute. Yeah, so clothes appear to be darker in color when they're wet. But that color change reverses as soon as the clothes dry. What's going on here? So most clothes appear to be matte because when light hits the surface, some of the light is sent through the fabric, which refracts, and some of it is sent back, but that would be undergoing diffuse rather than specular reflection. When clothes are wet, now you have a layer of water on top of the layer of fabric. So the light has to pass through water and then through the fabric, which causes more light to be refracted into the fabric and less light to be reflected back into our eyes. And so since our eyes are registering less light, the object appears to be darker. Alrighty, so tune in for our next video about the particle properties of light.